Alright, in this video we're going to analyze functions with successive differences. Successive means in a row, and differences means to subtract. So just a couple vocabs and examples, it should go pretty quick. The first successive difference is the values you get when you subtract the successive y values. So basically you have a list of y values, you find the difference between each one and you write that down as another list of numbers, and then you look at those differences. And then the second successive difference is the difference in the list of first successive differences. So let me just create some crazy little table here. Suppose you have an x, y, t table, and you go 0, 1, 2, 3, 4, and 5. And I'm just going to make up some random numbers here. 2, 6, 10, 11, 15, 20. Okay? So this would be the first difference. You could make another column on your table, the first difference. Okay, so you can't actually get a first difference for the first thing in your table because you don't know what was before it. But so this one you can't fill anything in. However, this one here, the first successive difference, is when you go from here to here, the difference is plus 4. Okay, so to get to here you did plus 4. To get from here to here, you did plus 4 again. To get from here to here, you did plus 1. To get from here to here, you did plus 4, and to get from here to here you did plus 5. So it turns out that finding patterns in the first successive difference will help enable you to identify what kind of function it is. For example, when we learned about arithmetic sequences, they had what was called a common difference, which means the first successive difference should always be the same. If it would have been 4 every time, that means that our function is just add 4 each time. Okay, the second successive difference, I think you can predict what it's going to be. Second difference, all right here. This one you can't figure out, and this one you can't figure out because you didn't have a term before it. But now you're looking at the second difference, which is the difference of the first difference. So from here to here, the difference is 0. From here to here, the difference is -3. From here to here, the difference is +3, and from here to here, the difference is 1. So it turns out that patterns in the second difference will also tell you a little bit of information about the function. So let's go ahead and look at that. Problem-solving tips. So if the first successive difference is constant, okay, that means you're getting the same value every time. What you have then is a linear function, just like we learned about before with a common difference. So that one's something we've covered before. Okay, if the first successive difference is changing, but the second successive difference is constant, then you have a quadratic function. Okay, so with a quadratic function, let me go back a slide. These would all be different, but this one would all be constant. It would have been the same number every time. If that happens, then you have a quadratic function, aka a parabola. If neither the first common difference, or the first successive difference, or the second successive difference is constant, then you can check for a common ratio. Remember, we learned about common ratios. If you have a common ratio, you have a geometric sequence, which leads to an exponential function. And so the three different things that we've learned about are linear functions, quadratic functions, and exponential functions. So you can take a t-table, an x, y t-table, or a bunch of data points, and you can test the first successive difference for a linear function. You can test the second successive difference for a quadratic function, and you can test the common ratio for an exponential function, and this will enable you to identify which type of function it is. Just a quick reminder of the three types that we've learned about. Linear functions can be modeled as y equals mx plus b. Quadratic functions can be modeled as y equals ax squared plus bx plus c. And exponential functions can be modeled as y equals a times b to the x power. Alright, let's do a couple of examples, and then we'll be finished with this quick section. Look for a pattern in each table, and determine which model best fits. So let's try to find the successive differences. Okay, from here to here, I did what? From 12 down to 3, this is -9. Okay, then we have, -9. Then we have -3. Then we have +3. Then we have +9. So the first difference, these are not constant, so therefore it must not be linear. Let's look at the second successive difference. From here to here, that's what? from -9 to -3, that's +6. From -3 to +3, that's +6. And from 3 to 9, that's +6. So the second successive difference was constant. What does that tell us? Second successive difference is constant. We have a quadratic function. Okay? Once we've identified that we have a quadratic function, we know it has to have the form y equals ax squared plus bx plus c. Now we can use these values to try to figure out what the equation is. Well, we can look right here at this point 0, 0. That's the y-intercept, right? So that means our c value has to be 0. Okay? Now let's think about the stretch factor. Stretch factor here. Normally a parabola would go from, and this is also the vertex, well, this is vertex. You can tell it's symmetrical on the left and the right. So this has to be the vertex 0, 0. And normally you would go over 1, up 4. Sorry, God, I can't talk. You'd normally go over 1, up 1, but we went over 1, up 3. So that means our a value has to be a 3. And because we're centered at 0, 0, our vertex is 0, 0. That means there's no b value at all, because the x-coordinate of the vertex is -b over 2a, but that equals 0, so b has to equal 0. So our equation is y equals 3x squared. And you can double check it by plugging in all your points, and of course, if you plug in 0, you get 0. If you plug in 1, 1 squared times 3 is 3. Plug in a 2, 2 squared is 4, 4 times 3 is 12. Okay, so that works. I know that was kind of quick, but hopefully it makes sense. Next one. Let's find the first common difference. From here to here is +3. From here to here is +3. From here to here, +3. From here to here, +3. The first common difference is constant, and so therefore we know this is a linear equation. So our formula is going to be y equals mx plus b. Let's look for the b value. In our data table we have this point 0, 1. That tells us b equals 1. And the slope is the common difference here. So m equals 3. So our equation is y equals 3x plus 1. Okay, there we go. Y equals 3x plus 1. It, of course, fits all these data points. Last one, let's find the first common difference. Oh, we got decimals here. This sucks. From 0.75 up to 3 is plus 2.75. From 3 up to 12 is going to be plus 9. From 12 to 48 is plus 36, and that's, wow, plus a big number. I'm not even sure. Okay, let's go for the second difference. From here to here, it looks like that's going to be plus 6.25, then plus 27, then plus a really big number. So neither the first successive difference nor the second successive difference was constant. So it's not linear and it's not quadratic. So let's check if there's a common ratio. Remember that the ratio is any term, say n, over any term before it, n minus 1. Okay, so we can do 3 over 0.75, and that's going to give us 4. Or we can do 12 over 3. That's going to give us 4. Or we can do 48 over 12. That's going to give us 4. Or we can do 182 over 48. That's going to give us 4. So the common ratio, every single time we multiplied by 4. So if we have a ratio equals 4, then our quadratic formula, y equals a times b to the x. Sorry, I said quadratic, I meant exponential. Our ratio is our base, which is right here, so b is 4. So this is going to be 4 to the x power. And when x is 0, 4 to the 0 is 1. And our output was still 3 there, so we need to multiply this whole thing by 3. So this was a quick way to show you how to find the type of function that it is by looking at first successive difference, second successive difference, or common ratio. And once you've identified what it is, you can find the slope and the intercept, or you can find the stretch factor, the b-value, and the y-intercept, or you can find the ratio and the multiplying coefficient here based on the data points that you have. I didn't go into a lot of detail, but it's kind of a skill that we've acquired gradually over the year, and I'm happy to help you more in detail later. Okay. The second thing you can do for these is graph the set of data points and then look at them and figure out whether it's linear, quadratic, or exponential. I'm not going to do these because I think it will save time by not doing them, but if you graph a bunch of data points and they're linear, of course they have to all line up like that, or maybe going downhill. If you graph them and they're quadratic, of course they should all, have a pattern like this. And if you graph them and they're exponential, they should all start off low and then shoot up, or maybe start off and shoot, down and flatten out. But on one side they'll go up, and on one side they'll be flat. With a quadratic it goes up on both sides, and with a linear it's straight line. So when you plot these points, it should be pretty clear to see which of these three it fits. And that's it for this section, identifying and finding the equations for these three things that we've learned about. Alrighty, I'll see you in class.